First of all, I want to say good afternoon to everyone. It is a great pleasure and an honor to be here with you today at the University of Novi Pazar. Before I start, I would like to express my sincere appreciation to the University of Novi Pazar, the rector, and in particular the Department of Economics and Computer Science and its head, Professor Dr. Denis Bajramović, for kindly allowing me to deliver this lecture and for their warm reception. On the other hand, I also want to thank my university, International Balkan University, for its continued support, as well as my mentor, Professor Dr. Ervin Domazet, for his valuable guidance and collaboration throughout my academic and research journey. Furthermore, I wish to acknowledge and sincerely thank all attendees here for dedicating their time to be present today. I hope that by the end of this lecture, you will have learned something new. As you can see, the title of this lecture today, it is really an honor to address you today in the first of all, I want to mention that I would like to today to speak with you in Bosnian or Serbian language, but please forgive me this time. Maybe the next time I can continue with Bosnian or Serbian, but today I will go ahead in English language. And as I mentioned, and as you can see from the first slide, the title of this presentation, of this lecture, Distributed Computing for Autonomous Systems, I think that almost all of us already knows a little bit what or what we understand with the word autonomous systems. And it is really a great pleasure for me to speak about this topic today. Because this is a highly relevant, modern and rapidly evolving topic in computer engineering and technology. Autonomous systems are becoming increasingly important in many fields, from transportation to robotics and smart infrastructure, and understanding their underlying computing principles is essential for future engineers. But before we continue with this topic, please allow me to introduce my academic background briefly. I want to mention here that I obtained my bachelor's degrees from Istanbul Commerce University, Department of Computer Engineering, where I first developed an obsession with intelligent systems and distributed architecture. Afterwards, I pursued my master's degrees in computer engineering, this time at International Balkan University, with a focus on advanced computing systems and embedded technologies. As for now, I am in my second year of my PhD studies, also at the same university, International Balkan University, Department of Computer Engineering. And my doctoral research is centered on the theoretical foundations and system-level design of secure decision-making in autonomous vehicles. This research explores how distributed computing principles that we will talk today and heterogeneous system architecture can contribute to more secure, reliable, and efficient autonomous driving environments. Also, here I want to mention that in today's lecture, I will seek to relate some of this research insights to the academic topics you study, in particular, illustrating the fundamental role that distributed computing plays in the development of autonomous systems, with a specific emphasis on self-driving cars. First, I wanted to describe a little bit what is distributed computing, what we understand when we hear this word. Before we talk about self-driving cars or autonomous itself systems in general, we first need to understand the concept of distributed computing. In simple terms, distributed computing means using multiple computers or using multiple processors that work together to perform a single but larger task. Each of these computers, or sometimes we can call them nodes, has its own resource, such as CPU, memory, and storage, but the the idea here is that they communicate with each other over a network to achieve a common goal. You can think of it is a team of workers. Each one does part of the job, but they constantly share information to stay synchronized. We use distributed systems every day, from Google search, Netflix, and cloud storages to complex scientific simulations and financial systems. The main advantages of distributed computing are scalability, fault tolerance, resource sharing, and parallelism. What we understand with scalability, it means that we can add more nodes to increase performance. The other one that I mentioned, fault tolerance, if one node fails, other continue to work. It should continue to work. Resource sharing, different devices can share data and processing tasks. And the last one, parallelism, means that many operations happen at the same time. All of them we have on the self-driving cars, and that's why I mentioned this one now, just to have a briefly description about this. However, we know that designing such systems is not easy. Everyone right now on the world face challenges like synchronization, communication delay, data consistency, and security. But these same challenges appear inside an autonomous vehicle because, in a sense, self-driving car is itself a distributed system on wheels. On my next slide, I put as a title, what are autonomous systems? The word autonomous, I know that we already know that one, but means self-governing or independent. In computer engineering, an autonomous system is a machine that can sense its environment, make decisions, and take actions, all without human input. Some examples I can mention here. We have self-driving cars right now. We have robots. We have smart city infrastructure. We have AI chatbots on different websites. We have autonomous drones and many, many other technologies. All these systems combine hardware, software, and intelligent sensors to observe the environment, algorithms to interpret data, and actuators to perform physical actions. On the other hand, a self-driving car, for instance, has cameras, LiDAR, radar, many sensors feeding data into different processing units. It continuously analyzes this data, decides how to move safely, and then controls the steering and brakes, all in real time. Here is the parallelism that I mentioned before. So when we think about autonomous system from a distributed computing perspective, we realize they depend on many computing elements working together. Some in the vehicle, some in the cloud, and some even communicating with nearby cars or infrastructure. That's where distributed computing becomes a key enabler. It allows all these components to collaborate efficiently and make safe, fast, and reliable decisions. And now, let we see the self-driving cars. What or where is the part of self-driving cars inside the autonomous systems and computing distributed? I go step by step just to understand the distributed computing, what they are. After that, autonomous system in general, and now self-driving cars as a specific case. A self-driving car, or sometimes we can call them autonomous vehicles, is a kind of vehicle capable of sensing its environment and moving safely with little or no human input. This kind of vehicles combines a wide range of technologies: sensors, artificial intelligence, machine learning, control systems, and even distributed computing. This main idea is simple. The car must constantly answer three fundamental questions: perception, decision, and action. The first one means, what's happening around me? The second question of the decision part is, what should I do next? And the last one, when the car needs to take action, means how do I safely perform that decision? To answer these questions, the car collects data from its sensors, which means that perception. Sensors, cameras, radar, LIDAR, GPSs, and all other sensors or ultra sensors that are inside the car, and process all this data in real time to make driving decisions. Depending on the level of autonomy as defined by the Society of Automotive Engineers, these kind of vehicles or vehicles in general can range from level 0 up to level 5. To the level 0, we have no automation vehicles, which means full human control. Level 1 and 2, driver assistance, like adaptive cruise control or lane keeping. Level 3, conditional automation, which means that a kind of car that can drive itself in specific situations, but the driver must be ready to intervene. Level 4, high automation. The car can handle most driving tasks, driver not required in most environments. And the level 5, the last one, full automation vehicles, or means with no steering wheel or pedals, complete self-driving in all conditions. But most of today's experimental and commercial systems are somewhere between and level 4. For example, right now we have some of them like Tesla Autopilot, we have Waymo, we have Cruise, we have and many other technologies. And the reason why is between level 1 and 2, level 2 to 4, is because everywhere right now, in every country, they don't allow us to have a few full no human control or without driver cars. In some cases, we have some taxi in US, but they are not allowed because the question is, if accidentally it's a traffic accident, the fault, who will get the fault? Will get the fault the software or the developers that did this job? And this is the reason, the main reason right now why they don't allow the level 5, which means full automation vehicles, to be part of our life. Now, distributed computing inside self-driving cars. Now that we have a general understanding of what self-driving cars are and what they aim to achieve, let's look at how distributed computing operates inside them. A self-driving car is one of the most complex examples of a distributed computing system. Inside a modern autonomous vehicle, there isn't just one computer controlling everything. Instead, there are many computing units, small processors, graphic process unit, FPGA, microcontrollers, all working together in a coordinated way. You can imagine this kind of car as a mobile data center, a collection of computing nodes connected through high-speed network that must cooperate in real time. Each of these nodes handles specific tasks. For example, some process sensor data like video streams from cameras or LIDAR scans. Others run AI algorithms that detect pedestrians or vehicles, and others perform control computations, such as deciding how to steer or accelerate. What makes all this possible is the distributed nature of the system, the ability to divide large, complex workloads among multiple processors that operate in parallel. Without distributed computing, it would be impossible, I can say, for a self-driving car to process all sensor data and make safe driving decisions within milliseconds. Let me mention some system layers inside a self-driving car, or the system layers of a self-driving car. The architecture of self-driving car can be divided into several computational layers, each responsible for specific function. First, we have sensor layer, which means that this layer includes itself cameras, LiDAR, radar, ultrasonic sensors, GPSs, and they constantly collect raw data about the vehicle's surroundings. The data volume is very huge. We can say that a single car can generate several terabytes per hour. The next one is perception layer, which means that right now, the collected data that we have from the sensor layer, we convert this data into useful information. Which means that this one can detect lines, objects, pedestrians, also the traffic signs, using machine learning models. Decision layer. One more thing I forgot to mention here to perception layer. This one runs on GPUs because they handle parallel image and signal processing efficiently. And this one is, I think that this one is really important for the students that are studying in computer engineering or computer sciences right now. Doesn't matter in bachelor or master or PhD studies. The third one, decision layer. This is where the car decides how to act. It performs path planning, collision avoidance, and motion control. These modules run on CPUs, not on GPUs, or sometimes maybe in dedicated AI chips. For example, NVIDIA drivers or Tesla FCD computers. Control layer. This one converts high-level decisions into low-level physical actions, controls steering, throttle, and braking using microcontrols. And it is important here also that this one must be highly reliable and deterministic. And the last one, cloud and edge layer, means that the car connects to external cloud servers or edge nodes for additional computing power, software updates sometimes, and sometimes for high-definition map synchronization. From here we can say that each layer performs a specific role, but they all depend on fast communication with each other and synchronization to make driving safe and efficient. Together, they form a distributed computing ecosystem inside the car. Another important topic inside self-driving cars is communication and cooperation. Communication with other cars and communication inside the car. Communication of the heterogeneous components, such as CPU with GPU, GPU with CPU, and both of them with the FPGAs. For this architecture to function, the different computing components must communicate and coordinate effectively. Data from sensors needs to reach the perception layer instantly. The perception output must be available to the decision layer with minimal delay, and the control layer must receive actuation commands at precise timing intervals. All this means the system operates under real-time constraints. Each process must finish within a strict deadline. And to make all of this possible, self-driving cars rely on middleware frameworks. I can mention two of them: robot operating systems and data distribution service. These two frameworks handle the message passing between software models. For example, here I can mention that let me imagine that the object detection module might publish messages like pedestrian detected at X, Y, while the planning model subscribes to those messages to update its driving strategy, and the communication extends beyond the vehicle itself. We have two communication inside this kind of vehicles: V2V, or vehicle to vehicle, and vehicle to infrastructure communication, which means that cars can share data about traffic, weather, and even road hazards. So, in a broader sense, distributed computing in self-driving cars happens not just inside one car, but between many cars and the surrounding environment, forming a network of intelligence. Sometimes we call them connected agents. Real-time and safety consideration. Now let's talk about real-time performance and safety, which are two fundamental challenges in distributed systems for autonomous driving. In self-driving cars, timing is everything. If a braking signal or steering decision arrives even a few milliseconds late, the result could be catastrophic. Therefore, every task is scheduled and prioritized according to its importance and urgency. The tasks inside the self-driving cars are divided in two categories. We have safety critical tasks and non-critical tasks. Safety critical tasks are like braking or obstacle avoidance, always take the highest priority. And the non-critical tasks such as cloud logging, software update, which are with lower priority. Another key concept here is fault tolerance. The system must continue operating safely even if one component fails. This is achieved through redundancy. For example, having multiple sensors or processors cross-checking each other. This kind of techniques come directly from distributed system principles: replication, consensus, and graceful degradation. In other words, self-driving cars apply the same reliability principles that are used in cloud systems or aerospace computing, but in much tighter, real-time environment. Now that we have seen how distributed computing powers self-driving cars, let's look at one of the biggest research challenges: how to make distributed decision-making secure and reliable. In a distributed autonomous system, decisions are not made by a single centralized unit. Instead, multiple computing models, often developed by different manufacturers, work together to reach a unified decision. This distributed architecture offers notable advantages in terms of efficiency, scalability, and fault tolerance, but it also introduces critical challenges related to security, synchronization, and trust. Now I will ask some questions to me first and to all of you. When we talk about self-driving cars, we need to ask ourselves three questions. How can we be sure that all nodes in the car are using the same version of data? What happens if one node is compromised or sends incorrect information? And how do we ensure that the final driving decision is consistent across all computing components? These are three questions. These three questions are the reason why I decided to choose this topic on my PhD studies. Specifically, on my doctoral studies, I aim to find, or maybe to, not to design, but let me say to find new methods and enable multiple heterogeneous components, CPUs, GPUs, and FPGAs, and external cloud nodes to cooperate in secure, synchronized, and deterministic manner during real-time decision-making processes in self-driving cars. About this one, I also wanted here to mention some, because I had the privilege of presenting a related study at an international scientific conference, MIPRO, held in Opatija, Croatia, Republic of Croatia, where our paper entitled Securing Heterogeneous Computing Architectures in Self-Driving Cars. The case is isolation, processor communication, and threat mitigation. The paper is right now published in the conference proceedings, and maybe you can find that one online. Let's look at a few of the main challenges that researchers and engineers face in this field. Communication security means that autonomous cars exchange large amounts of data internally and externally. This data must be encrypted, authenticated, and verified to prevent tampering or attacks. The other one is data consistency. Each computing node must have access to the same reliable information. Synchronizing data in real time is difficult when sensors and processors operate at different rates. The third one, fault tolerance and redundancy, that one that we mentioned. Distributed system must handle hardware or software faults gracefully. The system must continue operating safely even if one node or one module fails. Timing and latency. Decision must be made under strict real-time deadlines. Any delay in communication or computation can lead to unsafe behavior. The fifth one is verification and validation, which means that we need to verify the correctness of distributed algorithms in real-world scenarios, and to base that one on open research or open sources that we have right now. Each of these challenges represents an ongoing research area combining knowledge from computer engineering, distributed systems, artificial intelligence, machine learning, and so on. Current autonomous vehicles typically employ CPUs, GPUs, and FPGAs as separate entities, each with fixed roles and no runtime task reallocation. Most existing security mechanisms insufficiently protected. Moreover, few studies propose full system architectures that integrate this aspect into one unified and coherent model. In addition, also here I wanted to mention another paper, my paper, of course that all of them, both of these papers we did together with my mentor. The name of the paper is Parallel Processing for Real-Time Decision Making in Self-Driving Cars. Also, this one is online right now. It is a conference, to be honest, held in Tirana, Canadian Institution of Technology, and you can find that one also online. The future of distributed computing for autonomous system is very exciting. Here are some directions where the field is heading. Future cars will not rely only on onboard computing. They will use edge servers and cloud platforms for large-scale computation, data sharing, and real-time updates. In future, cars will train AI models collaboratively without sharing raw data. This can improve privacy and scalability. Blockchain technologies are being explored for secure communication and data integrity between vehicle-to-vehicle communication and vehicle-to-infrastructure. Experimental computing models like neuromorphic processors or quantum algorithms could drastically reduce latency and power consumption in distributed AV systems. And the last one, beyond technology, researchers are also studying accountability, ethics, and responsibility in autonomous decision-making. All of these directions show that distributed computing is not just a technical necessity. It is the foundation for the next generation of intelligent and trustworthy autonomous systems. To summarize, we started from the basic, distributed computing and autonomous systems. And we saw how these two concepts intersect inside self-driving cars. We explored how sensors, processors, and communication frameworks come together to form a distributed architecture capable of real-time decision making. Finally, we connected this with ongoing research in secure, trustworthy, distributed decision making, the area where I am focusing my PhD studies. And at the end, I can say that I hope this lecture has given you a clearer view of how computer engineering concepts are applied in real world, and perhaps inspired some of you to explore this field further, whether in distributed systems, in distributed computing, in artificial intelligence, in machine learning, or maybe in autonomous technologies in general. Thank you very much for your attention. And if you have any question, I am open for that.
Many thanks to Nesili for
Thank
this
you.
lecture, for this one topic that will be very important
Hope so.
in the future, that is very near to us.
Yes.
Maybe
Yes.
we think that is far, but it is more near than we think.
Yeah.
So, dear students, do you have some question for our lectures? Anyone? First time, second?
Maybe I can share also here my email and my LinkedIn account. Maybe we can contact each other through them for some questions or.
Many
Yeah.
thanks. Let's say students.
Yes.
How do you think that will the government force you to use self-drive? And I tell you that will force you. Do you have an answer?
Cut the petrol.
Cut the petrol. Okay, that will be one way. But main thing is insurance. Insurance will be much high if you want to drive yourself. And insurance, if will be autonomous drive, will be maybe 0 or something like that. And with that particular way, government will force us in 10 years, 20 years to use much of autonomous drive. Do you have some other question? Maybe no.
I have a question.
Yeah, sure.
I think the main reason why people don't like electric cars is because they don't believe that they are safe or something like that. So what are the odds for the car to have like a bug or something to go wrong?
To be honest, right now, I can say that I'm also coming from North Macedonia. I did some research and most of people, not that the reason is not that they don't believe on self-driving or autonomous cars. They don't believe in our roads that we have. Everyone says that if I bought a Tesla and put it in an autonomous system, it will go inside the house and will go in another way. This is the main reason right now that I got multiple answers like this. But I think that this is not, they don't have a clear or correct information about this one. And no one is talking about this because it is like we are Balkan countries and we don't need to talk for this one because Americans will do this for us, Europeans will do this for us, and so on. And that's why we are going back and say, okay, then we will get some information from them, and that's all. I also want to share one of my experience when I was at MIPRO conference at Opatija. After I present my paper, one professor there asked me, where are you from? I mentioned North Macedonia. We are north now. And he asked, self-driving cars in North Macedonia? This was a question, but to be honest, I didn't like that question because I'm not trying to do a new self-driving car in Macedonia. I'm just trying to a little bit to explore what we have inside this type of cars, how they communicate, because we have computers inside, we have nodes inside, we have CPUs, we have GPUs, all of these that we are using every day as a computer engineering students. And when we talk about self-driving cars, no, I don't know. And this is I don't know if I answered your question, but I wanted to share this up. Thank you.
That is good question, but we cannot connect self-drive just with electric cars, because BAG, Beyond Dreams, Chinese company, have also cars who is on petrol.
Yes.
And they also have full self-drive, full self-parking, full self, I don't know what else. So, other one question. Just one point that Nasimi pointed. European Union doesn't allow full self-drive because one legal issue is if a car needs to hit some car or kill a pedestrian, what will full self-drive do? And that is the question that the European Union asked Tesla. Tesla had a product factory in Germany, isn't it? Near Berlin or something near. Yes. But they don't sell full self-drive in Europe, but they selling in UK, in USA, in other part
of the world.
So many thanks.
Thank you very much. It was a really pleasure for me to be here with you today.
For this lecture, and I will hope that some of our students will be now interested.
Hope so.
For that.
Hope so.
Because just one thing, we have one, let's say, a guy from Novi Pazar is chief executive officer of Stellantis, and he is interested in that our students be part of Stellantis, of research, and you must alone take this way to explore and to be science in some way of that. Many thanks.
Thank you again. Thank you again. Pleasure for me.
That will be.
Thank you. Thank you very much. Pleasure for me. Pleasure for me. Thank you.